Good day, ladies and gentlemen. This is our lecture number 4, and we will start looking at oscilloscope. As we all know, the oscilloscope is one of the electronics measurement devices, and previously we have analog available, and of course our discussion on the cathode ray tube. One of the applications of that tube is in oscilloscope. But today, most of the oscilloscope available, they are digital in nature, and we know the reason, because digital signal has so many advantages over the analog. And for us to start with, let us look at the block diagram, the oscilloscope, digital oscilloscope. As you can see here, I have two images. The first one is the picture of the front panel of the oscilloscope, while the other one is the block diagram showing the different components or different stages available in digital oscilloscope. So if you look at it, we have two channels, meaning this oscilloscope can be used for measuring two signals at the same time, especially when you are going to be doing mathematical operations on the signal, like summing, like difference, integration, and what have you. And attached to each of these two channels, we have what we call the signal or the impedance matching network. And we know the function of this is to match the impedance of the input and that of the point at which we deliver the signal to the oscilloscope. And on each of the channels, we have an amplifier, G, and the function of this amplifier is to boost the amplitude maybe of the signal taken at the inputs of each of the channels. And after doing that, because we are dealing with digital oscilloscope, then the signals will be sampled now. That is, we start the process of changing the analog to the digital, and we know the first thing is to take samples. And of course, even before taking the samples, we do have a filter. It's a band pass filter. Its function is to make sure that only signals within that range of frequencies will be allowed to pass. And after that, it will now be processed, and it will be delivered to the memory stage. That is, whenever the sampling is done, we'll first of all keep the signal in the sample in the memory, and after that, the same signal, the sample signal, will now be quantized. We apply some clocks in such a way that those discrete values will now start changing to digital values, and that is completed at this point where we have a clock. Its function is to give us the digital output. As you can see, this waveform is for zeros and ones, and the output of that will now be passed through a time-based circuit. Its function is now to modify the signal in such a way that whatever amplitude will be seen, it will be with respect to the amplitude, with the time on the horizontal axis. And when that is done, the signal is further conditioned, and it will be sent to the display unit. Now, all these things I have said, they are exactly what they are supposed to be here. Here we said the first thing is to use a particular coupling method. You can couple it using DC, or sometimes you can combine AC and some part DC. That's why we say AC, a part link. And now the signals, as I told you, after passing through the matching network, they will be sent to the amplifier G, and after that the samples will be taken. The moment you do that, that CAN device you've seen, its function is to start changing those discrete signals from the sample and hold circuit into the digital values. And we use 8-bit accuracy. You can have another one maybe with 16 or 32, but the most commonly used is 8-bit accuracy. We have discussed this circuit. And then, what are the criteria that we use when operating a fixed frequency oscilloscope. The first one is the analog signal will be passed through a bandpass filter, as I've said. Its function is to make sure that only that range of frequency is allowed. After that, it will be taken to the sample and hold circuit, where the continuous analog signal will be broken into discrete form. Now, in some cases, we use time rise as one of the methods of taking the sample, but in reality, that one is not mostly used. And the sampling can be carried out in different ways. The first thing is you can do your sampling in real time. That is to take some samples in every single circuit. And sometimes you can take it in such a way that you have a sequential and random mode. That is, in this first cycle of our analog waveform, maybe you take 5 samples. In the next one, you decided to take 1. In the next one, you take 10 in a random way. But in reality, the first method is the most commonly used. And whenever you want to use that commonly used method, you just respect the Nyquist-Shannon theorem. And what this theorem is saying is that the sampling frequency must be greater than 2 times the maximum frequency in the analog signal. But if you want to do it in that sequential or random mode, then you have to use this formula for calculating the sampling frequency. It is equal to Kr times the bandwidth, where Kr is a constant. Its value is 2.5 when you are dealing with sinusoidal signal, but if you are dealing with the transient signal, then it will be around 4. That is, it is even more than that of the Shannon theorem. Now, after the analog to digital conversion, as we have seen in the diagram, the signal will now be stored in the memory. As you can see, each channel has its own memory terminal. And the visualization of the signal, which is modulated, it will now be visualized in form of what? Amplitude with respect to the time on the horizontal. Or sometimes it can be angular with respect to what? Time on the horizontal axis. And the reason why we do that is that we have multiple frequencies, because I told you we have a band pass filter that will take between the minimum and the maximum. So whenever you want to display the signal, it has to be either amplitude on the vertical axis and the time on the horizontal axis as usual, or the angular modulation, where some angles will be displayed on the vertical axis. And whenever we are using that single circuit, we said that's the traditional, the one which respects the Shannon theorem, that the sampling frequency must be greater than twice the bandwidth of the signal. Then this one, it has to be done with respect to that Shannon theorem. Now, whenever you want to use any circuit, of course, we have what we call one of the principles of calculation in electronic circuit is what we call the maximum power transfer theorem. And what this theorem is saying is that whenever you are transferring energy from one point to another, you have to make sure that the impedance of the producer and the impedance of the collecting end, they must be the same, they will be matched, so that a maximum signal can be now transferred. Now, the standard impedance matching network used for us is given here. As you can see, I have resistor and a capacitor in parallel to one another, and the input resistance of the oscilloscope normally is 1 mega ohm. That is the normalized value. So this oscilloscope, as we have seen, it has a very high bandwidth, because I told you we use a bandpass filter. So most of these digital oscilloscope, they have a bandwidth of around 500 megahertz, and of course sometimes they can use 50 ohm as their standard impedance as the input. So now if you look at this, 1 mega ohm and 50 ohm they are far away from one another, and of course the maximum power transfer theorem is not respected, so that we cannot have maximum power transfer. So how do we do? What do we do in order to match the two? What we normally do is to come up with the complete matching network. And this, if you look at this diagram, we have two sections. This one is the impedance matching network for the inputs, and this one is the internal in the oscilloscope itself. So you can see in each case we have a resistor and what, a capacitor, and in each case they are parallel to one another. So for the inputs, that is the input, not the oscilloscope, the value of this capacitor is around 15 picofarads, and of course it varies between 10 and 20, but we normally take the middle one, 15. And the measurements they are normally done using coaxial cable, and this coaxial cable also they have their input line capacitance of around 100 picofarad for every meter of the coaxial cable. So if we want to match the two, we can say the total a capacitor should be equal to that 15 plus d times 100, where d stands for the distance. If it is 1 meter, then it is 100 picofarad, and if it is less than that, you put whatever is your d. So the d is the length of the cable, as I have mentioned, and whenever it is equal to 1 meter, definitely we end up having 115. So if you want to resolve this problem in order to match the impedance of the input terminal and the internal impedance of the oscilloscope, we have to do some mathematics. And for you to do that, you use what we call you take the transfer function. Whoever did control at any level, definitely he knows what is a transfer function. And the transfer function is giving us the ratio of the two voltages, that is the voltage at the input terminal and the voltage at or inside the oscilloscope itself, and it is given by this complex formula. And nevertheless, nobody will ask you to drive it, but this is the formula that will give us the final impedance or the transfer function. Now, if you want to proceed from here to simplify this, then you have to assume that your filter is all pass filter, and if you do that, definitely we will finally have a relation like this, that is RSO CSO is equal to Rin Cin, that is comparing those of the input terminal, that's the coaxial cable, and those of the internal of the oscilloscope itself. Now you can see that this one is a very simplified function with respect to what we have here. Now if we progress, we'll now also find out that the impedance of the measurement is finally going to be equivalent to this, that is Rs naught plus Rin all over 1 plus J Rin Cin and times omega, where the omega is the angular frequency. You should remember the capacitance or reactance of a capacitor, definitely it is always a complex, that is why this J comes into the play. So now we can see the impedance is now equivalent to this, which are in a parallel with the capacitor, because as you can see here, this one is like it is in parallel with this, if you can remember our circuit theory. Now the value of that capacitance is given by this Rin all over Rs naught plus Rin times what Cin, where the Cin we have already seen it in that formula, and that Cin is the total capacitance of the coaxial cable, which itself is always smaller. It is very small value, which about 50 ohm. And the reason why we are doing all these mathematical evaluations is to make sure that the input resistance of the oscilloscope, which is about 1 mega ohm, is now matched to the input impedance of the coaxial terminal, which is around 50 ohm. Now after doing that, we go to the next stage, that is to see what type of measurements can we do with an oscilloscope. Definitely oscilloscope, the signal, as we have already seen, it is displayed in digital form, and definitely it also have some different aspect of measurement that it can do. The first one, we can use it in measuring voltages, and the voltages of different types. For instance, we can measure a peak voltage, that's the highest possible voltage in any signal. We can also use it to measure the effective voltage or the average voltage. And of course, we can use it to find the final value of any voltage, the high or the low voltage. And we can also use it to find the squared signal, that is root mean square value of an alternating AC signal. Another measurement that we can do with the oscilloscope is we can use what we call the temporal measurement. If we say temporal, we are referring to those signals that are a function of a time. And among them, we have a period, it has to do with time. We have frequency, it also has to do with time. We can use the oscilloscope to find the rise time and the fall time of any signal. And of course, we can use the oscilloscope for the third category, that is in mathematical functions. For instance, we can use it to find the sum of two signals, to find the difference, and of course, we can use it for a past Fourier transform. And this involves the calculations, like the coefficient of differential and the coefficient of what? Integral available in any signal. So basically, oscilloscope has three basic functions: in voltage, in temporal, that's with time, and in mathematical operations. The difference is that in oscilloscope, we display the amplitude of the signal on the vertical axis and the time on the horizontal axis. So we can say oscilloscope is analyzing in time domain. But in spectrum analyzer, the reverse is the case. That is, the amplitude is on the vertical axis, just like the oscilloscope, but the horizontal axis, instead of being time, it is now a frequency. So we use the spectrum analyzer in order to visualize the properties of the signal with respect to the frequencies of operation. So there are basically two different methods in which the spectrum analyzer is used. The first one is taking our measurement by setting the center frequency. That is to say, whenever you want to use the spectrum analyzer to analyze any signal from any circuit, you now select the center of the spectrum analyzer to be the midpoint of the range of frequencies you want to measure. So if you do that, you will see that whatever, let's say the bandwidth of your signal, let's say is 20, that is from 0 to 20. Now you select 10 to be your center frequency, so that on the left hand side you can see any frequency below the center, and on the right hand side you can see those frequencies above the center. That is to monitor the signal, the signal on different or on both sides. Now the other way, instead of using the center frequency, we use upper and lower frequencies. So in this case, we now set what is the lowest frequency and what is the highest frequency. And of course, this range of frequencies between the start and the stop is our range, or the span of the frequency on which the measurement is being taken. So there are also two methods of carrying out frequency analysis using the signal analyzer or spectrum analyzer. And the first one is those analysis for circuit or for systems that we categorize as low frequency, and this is any frequency from 1 up to 100 kilohertz. And in this case, we use the analyzer based on what we call the Fourier transform analysis. What this means is we are going to take the signal and apply some mathematical expression to it in such a way that it will transform it into what we call the fast Fourier analysis. And the details of this is coming when we are going to look at the two circuits of general spectrum analyzer. So the second one, we call them a radio frequency, and these are the frequencies ranging from that maximum of the other one, that is 100 kilohertz, up to 100 gigahertz. And these frequencies, we either call them high frequencies or microwaves, and they are carried out using what we call the sweeping spectrum analyzer, while the other one is using the fast Fourier transform. We're going to see the two very soon. Now let us start looking at this sweeping spectrum analyzer, the ones that are used for the high frequency category we have seen here. And how does it work? This sweeping spectrum analyzer it is similar or even equal to the Heterodyne radio receiver. If you can remember your communication theory, maybe at 400 level we have a course for authoring, and this is the one that talks about the basic components of communication systems. So we have what we call the Heterodyne radio receiver. And how does it work? This heterodyne nature, instead of taking what we call the tunable filter, that is a filter that can be used for a range of frequencies, we rather use what we call the pass spectrum through a fixed filter. Look at this diagram. The first thing, if you look at it here, we have attenuator, and of course sometimes this attenuator can be an amplifier, because the function of this is to make sure that the input signal is within the range of amplitude that our spectrum analyzer can handle. So if it is high, we use attenuator to reduce it, and when it is very low, then we use amplifier to raise it. This is the amplifier. So this filter we're talking about, it is here. Its function is to make sure that it allows up to certain frequency to pass. Anything higher than that, it will block it. Now, the output of this fixed filter is now combined with another frequency, which is obtained from this ramp generator, and it is operated using what we call the local oscillator. So here is a summer, or it is a point where we combine the output of this filter and the signal from this ramp, which is essentially our local oscillator. Now the two will come out and they will pass through another filter, and this filter, it is what we call a frequency selective filter or central frequency selective filter. It is represented by this IF. The IF stands for intermediate frequency. It is selecting the intermediate frequency output from these two combined, and it will pass it. After passing through this filter, then there will be a detector. The detector is the one that will detect or identify all the components of the original signal we are taking from this input, and it will also pass through another filter circuit. After this filtration, then the result will be displayed on the screen. Now, the most important unit in that block diagram we have seen is the mixer, because this mixer is the one that will combine the RF input and that from the local oscillator, and it will give us certain levels which can be detected. Whenever the signal is very low or very high, as I said, we should attenuate it, and when it is very high, we'll now very low, we can amplify it. Now, this level of the mixer, where we have combination of the signal from the RF and the local oscillator, in some cases we can have many stages. That is, instead of using only one stage, we can have many. And the reason why of using more than one is to get optimal, that is the best output within the range of that frequency that we are doing our measurements. Now, each stage, in a situation where we have many stages, each stage will have its own mixer, the local oscillator, and it will have that intermediary frequency filter, that is IF filter. And with recent development in this instrumentation, we see that the last stage of the digital filter, it is, of that filter is always a digital in nature. That is, even if the signal that is being measured is analog, there is an inbuilt analog to digital converter that will now change it to digital, so that our if stage, that is intermediate frequency stage, will have high stability by using this digital filter. And of course, it will have a very good resolution even when the frequency is as low as 1 Hz. So that's the reason why the last one is always made a digital filter, even if the previous ones are not digital in nature. So in this case, you find that the final section of is digital, as I explained, and that final section, apart from the filter, it have that detector also. If we can go back here, I told you after this if, we have a detector. So that final detector is also a digital in nature, and of course our display control, it is controlled by digital circuits. So after using your selective filter to filter out those frequencies which are not needed and pass those that are allowed, then your peak detector will now find the amplitude of the selected lines. What you mean by the selected lines? Components of the signal on the measurement that can be displayed on the screen. Then before displaying on the screen, definitely there is another filtration. If we go back to the diagram, you see after detecting, we have another filter. So it has to be filtered before we finally display it on the screen for visualization. And in recent time, we have some microprocessing variations where this signal, it is digitized after what we call the video filtering. Video filtering is also a stage or it's a process of filtering the signal so that we can have a very good display on the screen, and that is done using microprocessor controls. And of course the local oscillator is the one that is combined with the original signal for us to get the final result accurately. Now, what are the main parameters that we regulate when operating spectrum analyzer? The first thing is the center frequency. The center frequency, if we are using the first format, as I told you, it has to be regulated and it has to be selected correctly. And the second one is the frequency span. When you are using start and stop, that is the lowest frequency and the highest frequency, this has to be regulated so that we have a very good result. And the next parameter that you have to actually regulate is the resolution. The resolution is nothing but the length of the selective filter. What is the bandwidth, the minimum and the highest it can capture? And this is represented by this, that's the bandwidth of the resolution. And it is compared, or it is related to another parameter. We call it a sweep rate. That is the number of times it can scan the whole spectrum. And this is the sweeping rate. And the two are represented by a formula where the sweeping rate is equal to square of the bandwidth of resolution all over this K subscript f, and this is a constant which depends on the type of filter we are using. When we are using the Gaussian filter, the approximate value of this K subscript f is equal to 2. Now, if you want to do the measurement also, as we have seen, definitely we have to do some adjustments on the detected amplitude, because I told you we have attenuator and of course we have amplifier. Depending on whether the signal is low to be amplified or is high to be attenuated. So we have to get the maximum value that can be displayed at the top of our screen. If we allow it to go more than what it can handle, then the result would not be displayed correctly. And the unit of this amplitude that can be detected, the maximum value, is either in volts or sometimes in dB, that is in decibel. And of course, if it is in decibel, we know that it has some variance. We have a dBV and we have dBm apart from the dB. Now, if the display is in dB, we know for you to change a signal from the normal form into the dB, you have to take a logarithm, that is logarithmic signal. So it is the one that is mostly used. Okay, so the sweeping, that is reading the signal number of times on the measurement, it is done normally by analog VCO. The VCO stands for voltage control oscillator. But now, most of the current ones, instead of using the VCO, they use what we call frequency synthesis devices, that is frequency generators or signal generators. And using these synthesis devices, it has advantage of increasing what we call the signal to noise ratio. That is the ratio of the correct signal all over the noise. So whenever this value is very high, it means the good signal is very high and the noise is very small. Now, we are done with that sweeping. The next one is the fast Fourier transform analysis, and it is given by this block diagram. As in the other case, we have attenuator, and of course I told you this is slash amplification, depending on whether to increase or to decrease. The output of this goes to the filter, which is analog in nature. After that, we go to sample and hold circuits. Its function is to break the continuous analog signal into discrete form. And then finally, we do our quantization on other processes in order to get our digital using analog to digital converter. Its output also has to pass through another filter in order to make sure that only allowed range is allowed to go to the FFT, which is the fast Fourier transform circuit. Its function is to read the magnitude of the signal and finally display it on the screen. And as we have said, this is just explanation of what I have said. We said we have either attenuate the signal or amplify. So as we said from the diagram of FFT analysis, there is the first point is attenuation or amplification, then filtering to avoid aliasing, and then it will be sampled. That's the first stage of digitizing, and finally the Fourier transform is produced after the ADC and the next filter. Now we need to remember excuse me, we need to remember the Shannon's theorem for sampling, which says the sampling frequency must be greater than twice the maximum frequency in the original analog signal. And this FFT analyzer, it has one advantage, that is it is very rapid, it is very fast, which means it can read all the components in one frequency cycle. And of course, if there is this speed, then we must have a very good resolution. That's the advantage of this speed. It has good resolution because of its speed. And another advantage is that it will allow us to obtain good resolution even when we are dealing with a very low frequency signals in hertz, not kilohertz or megahertz. And of course, this is very impossible if we are dealing with the sweep analyzer we have seen before. Now, what are the areas, the main areas of application of spectrum analyzer? The first one, it is used for studying the spectral nature of any circuit. For instance, if you have any circuit that have a signal, AM or FM signal, oscillator or anything, you can use it. You can use the spectrum analyzer to see the behavior of that circuit with respect to its operating frequencies. And of course, this helps us to establish what we call spectral dimension. What do you mean by this? Spectral dimension is the frequency-based behavior of that system. And of course, another main application of the spectrum analyzer is that there are some that have demodulation function, meaning when they receive RF signal, they can demodulate it, that is to separate the intelligence from the carrier frequency so that each one of them can be studied separately. And when we are dealing with an amplifier, the spectrum analyzer will allow you to do so many measurements on it. For instance, you can measure the harmonic distortion in an amplifier when it is operating. And this harmonic distortion is just an indication of the energy content in the fundamental frequency of operation of that amplifier and the harmonics, that's the multiples of that frequency. Though this analysis comparing the energy in the fundamental frequency and in the harmonics, it is expressed in percentages, but the number of harmonics are limited. For instance, in some you can analyze up to maybe 4 second third harmonic and something like that. It is not an infinite, it has a limit. And spectrum analyzer is also very important when you are doing a measurement that concerns what we call the spectral density, power spectral density. And the power spectral density is nothing but the amount of signal, the amplitude of signal per unit frequency, per unit hertz. For instance, you can find volts per hertz if your amplitude is in volts. And you can also find dB per hertz if you are expressing your energy in decibel. And this measurement, it helps us to do a measurement independent of the span. What do you mean by this? At any point of frequency, you can visualize the amount of energy or power available, not for the whole range of the operating signal of the circuit. And also in our studies of oscillators, you need another type of the measurement to be carried out using the spectrum analyzer, and this measurement is what they call phase noise. They call it phase noise, and the phase noise is just a indication also that can be that can be encoded, that is, it can be included when analyzing any oscillator so that you can see its spectral purity. What do you mean by spectral purity is how regular is the waveform that the oscillator is producing. It can be done on spectrum analyzer. Now, the next thing is whenever we operate spectrum analyzer, we need to be able to adjust the gain. And this gain can be adjusted using two controls. The first one is the RF attenuator. If you can remember, we said whenever you take an RF signal, after passing through before it passes through anything, it will go through an attenuator to make sure that the amplitude is within the allowed level. And this is very important because it helps us to protect the spectrum analyzer from being damaged, because if the amplitude is very high, that is what we call overloading. So we make sure we do this attenuation before you deliver the signal to the mixer. Then the other control is the if gain, that is intermediate frequency gain, and this is controlling also the amplitude that come out from the mixer. This one is after the mixer, because if you go back to our diagram, you will see that we have our of course, let me go back to the first one. This one, you can see that it is after the mixer that we have the if filter. So therefore, this is done after the filter. But for the attenuation, is the first thing before we go to the mixing level. And this control of the if stages, it enables us to control the signal, and we can control it by placing it exactly where we want it to be on our vertical axis. I have already explained two methods. You either use the central frequency approach, or you use the start and stop approach. You have seen it in the previous slides. Now, the filter bandwidth. This is another control of the spectrum analyzer, and it is done in order to determine the bandwidth of the unit, that is, of the signal that is being operated or that is being visualized. And for you to do this bandwidth filter controls, we have two approaches. The first one is based on the if bandwidth, and the second one is on video bandwidth. The if filter, that is the intermediate frequency filter, sometimes we call it resolution bandwidth filter, and we adjust it in order to adjust the resolution of the spectrum analyzer with respect to the frequency. And the video bandwidth, this is also filters that are used in order to give us ability to average our signal, that is, combine all the ranges of the signal and take their average. Now, after that, we have what we call the scan rate. The scanning is nothing but the rate at which the spectrum analyzer can read the whole signal and detect the different levels that are to be displayed on the screen. And this spectrum analyzer, as I said, they are operating by scanning the required frequency under our visualization. And the speed at which this scanning is done is very, very important. The reason is that whenever the speed is very slow, it is telling us that the measurement will take a very long time before it can be completed. So the higher the scan rate, the faster the operation of the spectrum analyzer. And as a result of this, we actually need to make sure that this scanning is done as a very fast possible rate. So this speed is limited by some factors. We want it to be very fast, but there are some limitations, and the limitations are given here. The first one is the if filter bandwidth. Whenever the bandwidth of this if filter is very small, that is whenever it is narrow, definitely the rate of scanning will also be very slow. This one thing. The second one is the video filter bandwidth. This is the one I told you we use it for averaging the signals. And also whenever this is narrow, that is the bandwidth of this video filter is narrow, the speed is also going to be slower. And the last one is the scan bandwidth. The scan bandwidth of any spectrum analyzer is the range of the frequency it is expected to read from the minimum to the maximum. So whenever this range is very large, it is very obvious that it will take a very long time to scan them one after the other. So if you can see these three parameters, the if bandwidth, the video filter bandwidth, and the scan bandwidth, they are the constraints, the limitations to the speed of scanning using spectrum analyzer. So what are we saying? We're saying that this if filter bandwidth, we should try to make it as big as possible, because the narrower it is, the slower it is. So which means the wider, the system will be very fast. The same thing with the video filter. Whenever it is narrow, the response should also be what? Very slow. But in case of scanning bandwidth, whenever the range of the frequencies to be scanned is very large, the scanning rate should be small. Which means if you can make your range of scanning to be as small as possible, it will make the operation of the spectrum analyzer very fast. And in order to do that, the spectrum analyzer is operated using what? Processors. Processors are integrated circuits, programmable, that can be used for operating so many other things. So the scan rate is high for filter settings. What we are saying here is whenever the speed of your processor is very high, definitely the scan rate is also going to be very high. Now, before we end our studies on spectrum analyzer, let us look at some hints. Let us look at some tips. That is some issues that we need to pay attention to in order to make sure our measurement is correct. The first one is we should beware of the input level of the signal from the circuit under measurement, because whenever the input is very high, we say it is overloaded, and that is one of the greatest factors that damage our spectrum analyzer. So you have to make sure that the spectrum analyzer, the input after the mixer, is within the limit so that it will not have a very high power that can destroy the spectrum analyzer. And this is the reason why we use an attenuator / amplifier from the first stage, so that to make sure the input level is within the limits. Then another hint is we should be sure or to find out where is the spore coming. Supposing you are taking measurement and the signal is not stable, it is random. That is what we call the spore. So you need to know, is the spore, that distortion, is it caused by the circuit we are testing, or is it internal to the spectrum analyzer itself? And the simplest way to do that is to reduce the sensitivity of your spectrum analyzer, for example, by 10 dB. Now, you visualize the signal level. If you find that the spurious signal is also reduced by 10 dB, now it is telling us that that spore, that distortion, is being generated from the unit under test, that is the circuit we are testing. But if you find out that it falls by more than 10 dB, then this is a problem that is from this spectrum analyzer itself. And the major reason that caused that is overloading the input. The first hint we gave you, so we have to look at that in order to make sure we are safe. The next one is you should wait for self-alignment. That is, whenever you start your spectrum analyzer, don't start taking measurement with it. You have to make sure that you give it time to go and do what we call the software booting. And apart from the software booting, it also undertakes some number of self-tests. And it will also do what we call calibration, so that it will be ready for use. But if you use it before that, whatever you get should be a wrong signal. It should not be correct. Then In doing power measurements with the spectrum analyzer, another hint is that we should know the accuracy of the spectrum analyzer when measuring power. It is very low if you compare it with that done using power meter. So if you get the accuracy very low, just know that that is the nature of the spectrum analyzer. It don't give high accuracy power measurement. So with this, thank you very much. This is the end of our lecture number 4. Please watch and watch as usual for you to understand it better. Thank you.